Okay, welcome back. So before I get started today, we are on a simulation break. Simulation break. Okay, let's talk about simulation for just a little bit. I just kind of squeeze this in when I can, and I'm really behind because I was working with some people who haven't ever programmed to get tutorials out and stuff. And so that's why I've been holding off on some of the simulation things I otherwise would have been talking about. So a quick break. So far, we only know how to simulate discrete random variables. And by the way, for specific distributions, there are often better things you can do than just interval chopping. But if this were a whole course on simulation, I sometimes teach that under the number APPM 7400. Then I'd go into a lot of detail like that. So yes, in all of these cases, there may be better things to do. But so far, all we've talked about are discrete random variables and interval chopping. And by the way, if you have a random variable that takes on the values like 1, 2, and 3, we had chopped up an interval and assigned values 1, 2, and 3 based on lengths that represented probabilities. And we grabbed a uniform, and when it falls in that interval, it will fall in each interval in the right proportion of times. So if you're still doing discrete and you have an infinite support, for example, the Poisson distribution, this is discrete and it can take on the value 0, 1, 2, 3, 4, on up. Obviously, you're not going to try to lay down all of these breaks in an interval. So if you were simulating a Poisson, if you had X Poisson with parameter lambda, then I would grab out of my random number generator a U that is uniformly distributed between 0 and 1. And I would look at the probability that X equals 0, and that is e to the minus lambda. And I'm going to call this P0. So I would put like P0 down, 0 down here and say, is U in there? If yes, great, assign the value 0. If not, I would add on the next probability, and that would be like a P0 plus P1. Is it in there? No. If it is, great. If not, add on another one. And so the point is you don't have to obviously lay out all of the intervals because there's an infinite number of them here. So you can just kind of recursively check. But that's not the point of today's simulation break. I want to do our first, oh, sorry. I don't know if anyone's writing that. I want to do our first example of simulating from a continuous distribution, and in particular, the exponential distribution. So we're going to use what is called the Inverse Cdf method. And this requires that A, you can write down a CDF, which we can't, for example, for the normal distribution, and B, you can invert it. So suppose that I have X, a continuous random variable with a CDF, a cumulative distribution function, capital F of X, which represents the cumulative probability that X is less than or equal to X. And further, suppose that this capital F is invertible. Now, I want to simulate values of X, and can I write down the CDF? Is it invertible? Maybe, maybe not. And if not, you go into the next thing, and the next thing, and the next thing. Our next algorithm is going to be the accept reject algorithm. And in that case, you want to be able to bound the target PDF with something. And if you can't do that, you go on to the next thing. And this is what keeps me in business as a Monte Carlo person and simulator, because there is definitely not a one size fits all thing. But if you can invert it, then you grab a uniform 0, 1 from your random number generator. I'm going to call it U. And then my claim is that F inverse of U, so this is a capital U, so this is a random quantity, has the same distribution as X. So if you want to produce values of X, you just produce values of U and shove them in this inverse function. And I would write this statement as F inverse U equals with a D over it for equal in distribution, X. So let's prove it. So this is a new random variable, and I'm going to call it Y. I'm going to let Y be F inverse of U. And let's look at the CDF, the cumulative distribution function for Y. So I'm going to denote it by a capital F sub Y of Y. And this is going to represent the probability that Y is less than or equal to Y. And all I know, the only information I have is that capital Y is this F inverse of U. So I'm going to plug it in. Nice and capital and random. And now CDFs are always non-decreasing. So they're kind of increasing, but they can flatten out. And that means that if I apply the CDF to both sides of this inequality, the inequality is going to hold. We're not going to flip anything. So I've got a smaller number and a larger number, and I'm putting them into an increasing function. So then I get a smaller number and a larger number. And if I apply F to both sides, then on the left side, I cancel the F and F inverse. And on the right, I get capital F of little y. So on the left, I have a random variable, and on the right, I have a variable stuck into a function, but it's not random. Okay, so the CDF is a probability. It's a cumulative probability, but in particular, it's a probability. So this guy is between 0 and 1 inclusive. And so we just need to know this probability for a uniform. So a uniform 0, 1 has a nice flat line PDF at a height of 1 because the total area under that curve needs to be 1. And we're just looking at, if you look at a particular value x and you want the probability the uniform is less than x, it's just x times 1. So the probability a uniform is less than or equal to x is x if x is between 0 and 1. And that's what I have going on at the top of the screen now. It's just that instead of little x, I have f of little y. So using the fact that I know the uniform CDF, we just wrote it down here, I just get f of y out of this. So that is exactly what I did over here, but I just did it over here. And what was capital F? It was our CDF for our random variable x. Sure, it has a y plugged in, but f was defined to be the CDF for x, so this is the probability that x is less than or equal to y. What did I start with? In conclusion, we have shown that the probability that y is less than or equal to y is the same as the probability that x is less than or equal to y. The CDFs for these two random variables are identical, and y was defined to be f inverse of u. And if you take the derivative of both sides with respect to little y, you'll get the PDFs for both, and they're identical. So maybe you feel a little better about that and saying they have the same distribution. So this is saying y has the same distribution as x. And y came from plugging a uniform into an inverse CDF. So as a quick, I don't know if this is an example. I'm not actually going to run a simulation in front of you, although I did just post some simulation notes today in today's module, along with the rest of the lecture notes for today. Suppose I have x exponential with rate lambda. So we know the CDF here. It is f of x equals 1 minus e to the minus lambda x. So if you call this y, and then you solve for x, you'll get x is minus 1 over lambda, the log of 1 minus y. So that's the inverse function. So f inverse of x, y, u, whatever you want to call it. I think I'm going to write it x again. F inverse of x is minus 1 over lambda, log of 1 minus x. So here is your algorithm. Step 1, you get somehow from your random number generator a uniform 0, 1, and then you output minus 1 over lambda log 1 minus the uniform. And that you are done. You have produced one exponential. And if you do that over and over and over again and make a histogram, you're going to start to see that exponential kind of shape, which I would do very well. That's not bad. And by the way, some of you already know this because after the last time we talked about simulation, some of you stayed after and we chatted a little more. But our method of interval slicing for simulating from a discrete distribution is really this inverse CDF method with a generalized inverse. And I don't want to bother to write it down, but for a discrete random variable, your CDF is a step function that jumps up by the appropriate probability oops, at every value that random variable can take on. And so if you grab, let me go to this picture here. This is a CDF. You're grabbing a uniform 0, 1 on this axis and going back to this axis. And so if you define a generalized inverse and what that even means, because this isn't invertible as is, but there is a generalized inverse for it, then that is equivalent to interval chopping. And I'd be happy to talk about that slower and in more detail with anyone who wants to, but I kind of don't want to do that in class. Okay, so one more thing on simulation, and that is simulating a Poisson process. So a Poisson process is a counting process. It's going to keep jumping up by 1 unit at random times. So if you have a Poisson process with rate lambda, we now know 2 ways we can simulate this. So this is time. And one is we can just start simulating exponentials as described above. So we can simulate T1, T2, etc., IID exponentials. And even that, there's some error, right? Whenever I talk about random numbers, someone always pipes up and says, "Don't you mean pseudo-random?" And yes, I do. These are, they come out of algorithms, but some of them are pretty darn good. And are they really independent? Yeah, they can fake it pretty well. So you just get some times, like maybe this is 1.7 and this is 0.6. Oh no, I have to add 7 and 6. So you would go out to 1.7 and then you would put another 0.6 on that, which is 2.3. Okay, I did it. You would just lay out these times and you would have a process that is flat and then jumps up by 1 every time you have an exponential time. This is kind of brutish, brute force. How you would simulate this really depends on what you want to do with it and if you're plugging it into something else, but we have one more method that we know about. Why does my chat keep disappearing? I see that I have messages and I can't bring it up. The second way that we right now, which is maybe not so elegant as well, so I would call this method 1. But another method, if you only care about a finite time horizon, is to use the fact that we know how to distribute events in a finite time horizon. So method 2 would be to fix a time. I really want to call this capital T, but that makes it look random, and it's not. So I'll just call it little t. And then you look at the interval from 0 to t, and you know how many events should appear there. It should be a Poisson number. So the number of events or x's, as I keep drawing them, is Poisson with parameter lambda times t. And that is a discrete distribution that we now know how to simulate from. And that would be doing, there are better ways, but that would be doing interval chopping and doing it gradually, right? Not trying to chop up the whole interval. So if you can simulate by interval chopping, right? You simulate x, a Poisson lambda t, and then that'll give you some numbers, like suppose it is 3, then you sprinkle them uniformly over this time interval. So you arrange, this is step 2, arrange them uniformly on the interval from 0 to t. So how might you do that? I would grab 3 uniform random numbers and I would multiply them by t. And that takes you from a uniform 0, 1 to a uniform 0, t, or maybe shorter if t is less than 1. Right? It just stretches things. And then I would put them in order. And this would be the minimum of those uniforms, the next largest, and the max. So that's another way to tell you when to step up in the Poisson process. I don't think either of these are interesting. Usually I use a Poisson process in the context of another problem where some other method of simulation might make more sense. Any questions on that before we get back to Markov? So I made a simulation document today where I have our interval chopping method and our inverse CDF method, and I've already put down our next method, which is going to be accept reject, that we're not going to do today, the accept reject algorithm due to von Neumann. And then after that, we're going to start doing methods involving Markov chains, and that's when we start calling it MCMC for Markov chain Monte Carlo. But now we're back to the Poisson process and definition 3 and little o's, small ones. All right. So I introduced you at the very end last time to little o notation, little o of, I'm going to say of h, but it could be of any letter. So a function f of h is little o of h, there's a better way to write that, if the limit as h, a positive number, goes down to 0 of f of h over h is 0. So the denominator is blowing up. So the only way this can go to 0 is if the numerator goes to 0. And it needs to be going fast enough to kill this denominator that is also trying to blow things up. And we'll do a bunch of examples, but we write, well, you could say, so you couldn't write that this is a little o of h, but mostly we're going to actually say that f of h equals little o of h, where this is like a really sloppy thing, but it's sort of like not, it's better than saying stuff that disappears. It's mathy notation, but it's still kind of a sloppy way just to wrap up things in a sum that are going to 0 kind of fast. And I have more to say about that, but let's look at some examples. So lambda h squared is, you know what, I'm going to do it like we do it. We actually write equals little o of h, since if you look at lambda h squared over h, you get lambda h, and that still goes to 0 as h goes to 0. So it's going to be useful for things at the end of like Taylor series expansions where you want to say, and that stuff goes away. And you might say, well, some of your other terms go away. And I'm going to say, yeah, but these go away faster in a little o of h kind of way. Because, for example, lambda h is not little o of h, right? Because if you divide it by h, you get lambda, and that is not going anywhere, much less 0. One we're going to need a lot in this class is e to the minus lambda h. So if you don't know it already, I think it's good for you to know that Taylor series or Maclaurin series approximation here. I'm just going to remind you down in the corner, e to the x can be written as the sum as n goes from 0 to infinity of x to the n over n factorial. And so using that, I'm going to write out the e to the minus lambda h as the n equals 0 term is 1. The next term is minus lambda h. The next term is positive lambda squared h squared, because really it was a minus lambda h that got squared over 2 factorial. I'm going to write just one more. What is my point? My point is that this E thing that we see all the time in exponential distributions and Poisson processes is 1 minus lambda h plus some stuff. That's little o of h. And little o of h functions don't have to be polynomials, but they mostly will be for us. And so things are going to be little o of h if they have, if the h has an exponent larger than 1. Right? Because if you divide h squared by h, you get h, and that still goes to 0 as h goes to 0. Does that make sense? Okay, so let's, I'm going to talk about some operations with little o of h functions, and then we're ready for our definition. Oh, yeah, MC. No. I used to go to a conference called MCM Ski, which was in Switzerland, and there was like 2 hours of conference scheduled per day, and otherwise everyone was skiing or lounging. But now they hold it. It was held in Switzerland for so many years, and now it's held in New Jersey, and they still keep the name because they want you to know it's the same conference, but it's really disappointing. Okay, so here I'm going to call this a little o of any letter, right? Obviously, I can use something else in place of h, so I'm just going to call this little o operations. So for my first trick, I'm going to say that little o of h plus little o of h is little o of h. What the heck does that mean? It's a notation. I would never say 2 times little o of h. It wouldn't be wrong, but it would be very weird because this represents possibly two different functions. So this represents like an f of h plus a g of h, where f of h over h is little o of h in that it goes to 0 as h goes to 0. And the same thing for g. So when you add 2 little o of h functions, f of h plus g of h, you get f plus g over single h, and this breaks up. And because the individual functions were little o of h, both of these go to 0 as h goes to 0. So what this line at the very top is saying is the sum of little o of h functions is again little o of h. You wouldn't be wrong to say 2 little o of h, but it's just not done. And the reason you wouldn't be wrong is because, and I'll come back and ask if there's a question on this, but if you have like a constant times a little o of h function, that's still a little o of h. Now, if you multiply by h's or functions of h, then you have to maybe think about it. But this is just like, multiplying your f of h times a constant, and it's still going to go to 0 as h goes to 0. So, before I go on, is there anything I can clear up with number 1? You're going to see me doing this constant thing with things that don't look like constants. So I'm going to keep this under example 2. For example, e to the negative lambda t times little o of h. This is a constant with respect to h. So this whole thing is still little o of h because it represents e to the minus lambda t times some function f of h. When you divide by h and let h go to 0, the f of h over h is going to 0. So the whole thing goes to 0. And there's nothing in the e that's going to cancel that because it's a constant with respect to h. All right. Just 2 more, and then we can get back to the Poisson process, and then we'll get more practice with this stuff. But little o of h times little o of h is little o of h. So to prove this, you really want to take 2 functions that are little o of h. So suppose f and g are little o of h. Then f of h times g of h over h, we can break this up into a couple of ways, f of h over h, and then g of h. So my first term there goes to 0 because f is little o of h. This goes to 0 as h, as h goes to 0. What? Now the g must as well, because remember our original definition, we're looking at a function that goes to 0 fast enough to kill an h going to 0 in the denominator. So a little o of h function necessarily goes to 0 on its own, which means this g of h must go to 0. Any little o of h function is going to 0. It's just, is it going fast enough? Is it going faster than a denominator of h? So here I took the product. I took the product divided by h. I rewrote it, and I noted that by definition, because f and g are little o of h, that this product divided by h goes to 0. So the product of little o of h functions is little o of h, and that is sort of represented like this. Like you wouldn't write little o of h times little o of h equals little o of h squared. Suppose you could, but really you don't. So we're going to do lots of calculations with Poisson processes where suddenly everything's just getting combined into this little o term at the end. And I love it because it's a way to kind of be sloppy, yeah, plus a remainder, but also you still look pretty mathy. Okay, one more example or non-example, and that is dividing. So little o of h divided by little o of h is not necessarily little o of h. As an example, I can look at the function h squared and h cubed. These are both little o of h functions because both of them, after division by h, still go to 0 as h goes to 0. So these are both little o of h, but if you look at h cubed over h squared, you'll get h, and this is not little o of h because if you divide by another h, it needs to go to 0 and it doesn't. So this is since h over h is 1, and that does not go to 0. Okay, any questions before we hit definition 3? You guys are so funny. Okay, definition 3 of the Poisson process. This is my favorite one. Our first definition had an I, double I, and triple I, and I was that we start at 0, which is really just a convention. Double I was that we have independent increments. And triple I of definition 1 was that the number of arrivals in an interval of time follows a Poisson distribution with some parameter lambda times the length of the time interval. Then we showed that that implied definition 2 and vice versa. And we replaced triple I there, the Poisson assumption, with the assumption of IID exponential inter-arrival times. And here's definition 3. So the counting process N of t is a Poisson process with rate lambda if and only if, this is the definition, three things hold. We're going to start it with 0 things counted at time 0. So if I need to prove these definitions are equivalent, I vote that I'm going to take the I because that's the exact same thing in all of them. Double I for both of our other definitions was independent increments. Now it's a little bit more. It is stationary and independent increments. So this is changing up a little bit. So this says if you're looking at some interval of length t, let's say this is S1 and this is like an S2 and S2 plus t, the number of arrivals in both of these intervals is identical. It stays the same as I move time. It's stationary in time. So in both cases, the number of arrivals I should see in those intervals is Poisson with parameter lambda times t. Now we got stationarity out of the Poisson triple I assumption from definition 1, and we got it from the exponentials as well. Although I didn't carefully write those out, but I was more careful in the notes. But here's where it gets good. My triple I here is not going to give us stationarity. That's why it had to be put into the list. So we have a couple of properties here, and that is the probability that n of t plus h. I don't know, stochastic people use h for small things that are going to 0. I have no idea why we don't use epsilon. We do for other things, but not for this. Okay, so n of t plus h minus n of t. The probability that this is 1, right? So this is talking about having exactly one arrival in an interval from t to t plus h. So the assumption for this definition is that this is lambda h plus little o of h. And it only kind of makes sense to talk about little o of h by following it up and saying that h is going to 0. So the interval has length h. And so our assumption here is that the probability of exactly one event in there is proportional to the length of the interval plus some stuff that's going away. In this case, the constant of proportionality is lambda. I don't think that looks like nearly enough. Well, I have more to say, but that's not a whole lot of structure. It's saying, okay, the probability of an event is proportional to the length of the time interval and some stuff going away. And to me, that doesn't look like a whole lot of structure. And that's something I keep saying in this class, that I think you can get the Poisson process out of pretty thin assumptions. So I'm not finished with double I. There's 2 ways I can write this. I'm going to say the number of arrivals in this interval from t to t plus h. This is greater than or equal to 2 with probability little o of h. The way to read that in English is as the interval shrinks, right? You start lowering the h and pushing it down. The probability of getting 2 arrivals is shrinking to 0, and it's shrinking kind of fast. The fastest, it's not like exponential, but it's faster than h is shrinking. So informally, we can get 2 or more events in an infinitesimal interval. We actually can't get 1 because things are continuous, but that's what the whole little o thing is about. And then the final thing you don't need, because we have this all wrapped up, but those 2 things imply, so I don't need this, but they imply that the probability that the number of arrivals in there is 0 So this, if you were to, I don't want to make this part of the definition. So I want to say the probability that this number of arrivals is 0, just being a little sloppy down here, is 1 minus the probability this number of arrivals is 1 minus the probability that the number of arrivals is greater than or equal to 2. And so that is 1 minus lambda h plus little o of h minus little o of h. And so I get 1 minus lambda h, and the rest of the stuff combines into just a little o of h. I don't want to cancel. It doesn't happen here because they're both negative. But you don't ever want to say little o of h minus little o of h is 0, because that's representing potentially two different functions. So you don't want to cancel them and do other things like that. So the moral here is this is 1 minus lambda h plus little o of h. And I could have used that. I need any two of these three conditions to fully specify triple I. I love this. It's so minimal. And yet we can get exponentials and Poissons out of this. So let's do it. Actually, not that interesting. First is that I want to show that definition 1 implies definition 3. The more interesting thing is, how do you get from the little o's to the Poisson? So let's look at definition 1 implies definition 3. This would be a little nicer if I had both definitions written. If we were in a classroom, I probably would use a sideboard and write all three definitions so we can point at them. But I'm going to say definition 1I is identical to definition 2I. I don't know if that makes sense. Just making up some notation. N of 0 equals 0. Definition 1I and definition 1 triple I. I'm sorry, the first one is double I, the second one is triple I. Implies definition. I'm not talking about definition 2 at all here. In the line above, I meant to talk about definition 3. It actually wasn't wrong, but it wasn't what I was trying to say. Okay, so definition 1, double I and triple I give us definition 3, double I. So definition 1, double I was independent increments, and that was just part of our double I here, which was independent and stationary. Definition 1, triple I was the whole Poisson assumption, but it was stated in a way that implied stationarity. And so stationary really came from triple I of definition 1. Right, okay, so we need to get the little o stuff out of definition 1. So definition 1, any part, this is going to imply the O of H stuff. As I was saying, this is the easy direction. Let's show it. So let's look at the, let's consider the probability that n of t plus h minus n of t is 1. And I want to show that I get the little o stuff from the Poisson stuff. So I'm assuming definition 1 holds, right? All of this. Assume definition 1 holds. Then definition 1 by stationarity, we have not that you need to do this step, but because it's stationary, this is the same thing as the probability that n of h is 1. It's just an interval of length h, so I've switched from t to t plus h back to 0 to h. And that was unnecessary because either one of these, I have that with the Poisson assumption of definition 1, this is e to the minus lambda h to the 0 over 0 factorial, which is just e to the minus lambda h. Yeah. No, I gotta plug in ones. I'm plugging in zeros, sorry. Plug in ones. With a 1 and 1 factorial. So this is lambda h e to the minus lambda h. And if you write out the Taylor series expression here. You get 1 minus lambda h plus lambda squared h squared over 2 factorial minus, and eventually I'm going to stop writing these tails because that's kind of the whole point of us having this little O notation to talk about a kind of tail of a sum. But when you multiply this out, you get lambda h minus lambda squared h squared, and that's little o of h. And the next term would be lambda cubed h cubed over 2 factorial, and that's little o of h. In other words, all of these things are higher powers of h than 1. So we get lambda h plus little o of h, and that's what we wanted. That's something that was specified in triple I of definition 3. So we're going from definition 1 to definition 3. So at this point, I would say, and you can, and similarly, the rest follow. But since we haven't spent much time with the little o of h, just for practice, let's look at, we only proved part of triple I of definition 3. So let's consider the probability that n of t plus h minus n of t is, I don't know. If we were together in a room, I'd have you vote on, do we want to go with 0 or greater than or equal to 2? I think I'm going to do greater than or equal to 2 because it will give us more practice combining little o of h functions. So assuming our original Poisson process definition, this is the probability that n of t, well, this isn't assuming anything yet, but this is the probability, no, sorry. I want to say it's 1 minus the probability of seeing it exactly 0 or exactly 2. This is 1 minus the probability n of t plus h minus n of t is 0 minus the probability. The same thing is 1. Now we're assuming definition 1 holds. So we know that this first thing is e to the minus lambda h, because h is the length of that interval, lambda h to the 0 over 0 factorial. No, you don't have to write that. I'm just afraid if I don't, someone's going to wonder where the other terms went. And then e to the minus lambda h to the 1 over 1 factorial. So I'm going to start rushing even more. Just get rid of the 0 stuff. Okay, so to simplify this, you could start writing out your Taylor series again, but we also already know that that e to the minus lambda h is actually 1 minus lambda h plus little o of h. I don't have to do that. I could just write these all out as series, but we do already know that. And then we have minus lambda h times a 1 minus lambda h plus little o of h. And so 1 cancels with the 1. Yeah, this is a positive lambda h cancels with this negative lambda h. What did I miss?
I think you want to distribute that second lambda h, so you get lambda squared. So you have an extra little o, and that'll go away.
Oh yeah, thank you. That's exactly right. So if you distribute this, you get lambda squared h squared plus little o of h, but h squared is little o of h, so this is another little o of h, and that's what we wanted to show. Love this stuff. Love sloppy but precise math. It's a cool dichotomy, and I'm out of time. So thank you. Homework 6 will be posted today. And yeah, thanks. Bye.